of Electrochemistry chapter. How to realize redox reaction. Redox reaction, as we explained, is a transfer of electron between two reactants. The first is the oxidant that has the capacity to gain electrons, and the second is reductant to lose electrons. Therefore, redox reaction have the potential to generate electricity due to the motion of the electrons in a wire. We have two ways to realize the reaction between the acceptor and the donor, between the oxidant, which is acceptor, and the donor, which is reductant. The first is the indirect contact, and this type of reaction produces electricity. So we need to separate the places of oxidation and reaction and reduction taking place. So we have two couples separated into two different beakers, and the two couples are related by a known way that will be explained later. So this is the formation of electrochemical cell. The second method is to do the direct contact between the oxidant and the reductant. But this reaction would not produce electricity, it will produce heat. The reaction takes place in the same beaker between the oxidant and reductant, and we will see these examples in the part redox titration. In the electrochemical cell, we have an electrochemical reaction that involves the transfer of electron, and therefore this is an oxidation reduction reaction. Consider the following reaction: MnO4 minus with Fe2 plus to produce Mn2 plus and Fe3 plus. The two couples oxrad involved are MnO4 minus, Mn2 plus, Fe3 plus, Fe2 plus. In this reaction, Fe2 plus is oxidized by the oxidant MnO4 minus, or MnO4 minus is reduced by the reductant Fe2 plus. So the electrons are transferred from the reductant Fe2 plus to the oxidant MnO4 minus, that are transformed respectively to Fe3 plus and Mn2 plus. If we want to realize an electrochemical reaction that produces electricity from this reaction, so we have to break this redox reaction into half reactions, one involving the oxidation and the second the reduction. The half reactions that can be written are the reduction. MnO4 minus gains 5 electrons in acidic medium and is transformed to Mn2 plus. The oxidation half reaction, Fe2 plus, lose 1 electron to be transformed to Fe3 plus. And as we know, in the redox reaction, the number of electrons gained should be equal to the number of electrons lost, so the oxidation half reaction should be multiplied by a factor 5. What is the meaning of this multiplication by 5? The multiplication of the oxidation half reaction by 5 indicates that this reaction must occur 5 times for each time the first half reaction, which is the reduction, occurs. So the balanced overall reaction is the sum of the half reactions. If we pass to the construction of the electrochemical cell from this reaction, we have to separate the two couples into two different beakers. In the first, we put MnO4 minus, Mn2 plus, and in the second, we have Fe3 plus, Fe2 plus. And we join these two beakers by a wire. So when we construct the apparatus as shown, no flow of electrons occurs. So what is the reason? In other words, if we construct this electrochemical cell by this way, we could not produce electricity. So what is the reason? In the beaker containing MnO4 minus, we have reduction. So MnO4 minus will decrease and Mn2 plus will increase in the solution, and the counter ion of MnO4 minus, which is K plus, remains constant. In the second beaker, we have oxidation. So Fe2 plus decrease in the solution, and the counter ion NO3 minus remains constant, and Fe3 plus will increase. So we will have violation of the electroneutrality principle that states the quantity of charge positive should be equal to the quantity of charge negative. So how to construct the electrochemical cell in this case? To construct the electrochemical cell, we have to solve the violation of the electroneutrality principle by adding a connection. This connection might involve a salt bridge, which is a U-tube filled with electrolyte containing positive ion and negative ion, or by using a porous disc in a tube connecting the two solutions. So we return to our example. We have two couples, MnO4 minus, Mn2 plus, Fe3 plus, Fe2 plus in two separate beakers, and connected by a wire, so the electrochemical cell did not function. We add the salt bridge. In case MnO4 minus decrease in the first beaker, so K plus ion positive will be greater. The salt bridge will send to the first beaker the negative ion in order to maintain the electroneutrality positive equal negative. At the same time, in the second beaker, the positive Fe2 plus decrease and the negative NO3 minus is greater than Fe2 plus. So the salt bridge will send positive ion to maintain the electroneutrality in the second beaker. We have two types of the electrochemical cell. The first is the electrolytic cell, are those in which electrical energy from the external source causes non-spontaneous chemical reaction to occur. So in the electrochemical cell, the redox reaction is non-spontaneous, we use external current to make this reaction spontaneous. And the second type is the voltaic cell or galvanic cell, or simply the batteries we use in our life, are those in which we have a redox reaction which is spontaneous and it will produce directly electricity. Drawing of electrochemical cell. Example, consider the reaction zinc plus Cu2 plus that gives zinc 2 plus Cu. First of all, we have to divide this global reaction into half reactions. On the left, we have the oxidation. So zinc is transformed to zinc 2 plus 2 electron. And on the right, we put the half reaction of reduction. So the transformation of Cu2 plus to Cu. The electrodes are the zinc metal and Cu metal and are surfaces on which oxidation and reduction have reaction occur. At the anode, as we said, we have the oxidation, so it's charged negatively by convention, and on the cathode is the reduction, and we put the charge plus. So in the drawing of the electrochemical cell, we have to take into consideration the presence of two beakers containing the corresponding solutions. Then we have to determine the anode, which is zinc in this case. We have to put the charge minus. The direction of the electrons is from the anode to the cathode, and the presence of the salt bridge, the wire, the direction, the cathode charged plus, and the direction of the current, which is inverse the direction of the electrons. In the electrochemical cell, the electrodes are connected by a wire that allow the circulation of electrons. The anode is made of a metal that is oxidized and represent the oxidation half reaction, and the cathode is made of another metal that is reduced, and this is the reduction half reaction. Consider, for example, a solution of FeC plus Fe2 plus, and we want to construct a galvanic cell by using this couple. So we have a couple oxide, which is FeC plus Fe2 plus, so this couple can be used in the electrochemical cell. The reductant Fe2 plus is not a metal, is an ion. And as we know, in the electrochemical cell, we need metallic electrode to be connected by a wire. So in this case, we use electrode of platinum, which is inert electrode to the electrochemistry, so it does not do any oxide reaction. And at the same time, this inert electrode plays the role of support of the reductant Fe2 plus, as shown in this figure. Previously, we drew the galvanic cell or the electrochemical cell, and we take into consideration the presence of the anode and the cathode, the salt bridge, the direction of the electron, and the direction of the current. We have another way to describe a galvanic cell, which is the cell notation, and this is a short description. The order or the sequence of the reductant and the oxidant is the following: red 1, line, ox 1, double lines, ox 2, red 2. The oxidation half cell on the left, the reduction half cell on the right. A single line is used as phase barrier between the red 1, ox 1 and ox 2, red 2. If in the solution we have multiple electrolytes in the same phase, we use a comma rather than the single line. Double lines means the salt bridge. In this example, the couple on the left is Fe2 plus Fe, and that on the right is MnO4 minus Mn2 plus. We have to use the sequence. We start by the red 1, which is Fe, then the ox 1, which is Fe2 plus, salt bridge. We pass to ox 2, which is MnO4 minus, and in the same phase we have multiple electrolytes, which are Mn2 plus and H plus. We separate them by a comma, single line, then red 2, which is the platinum electrode, the inert electrode. On the left, there is oxidation. We put the charge minus. On the right, reduction with the charge plus. So the cell notation can be described by the letter W, Fe, line Fe2 plus, salt bridge, MnO4 minus, Mn2 plus, H plus, line, platinum. This is the W letter. Cell potential and standard state. A galvanic cell consists of oxidizing agent in one compartment that pulls electrons through a wire from a reducing agent in the other compartment. The pull or the driving force on the electrons is called the cell potential, E of the cell, or the electromotive force, EMF, of the cell. By definition, the cell potential, E cell or EMF, is the difference in potential energy between the couples at the anode and that at the cathode. So E of the cell is equal by definition E ox red at the reduction minus E ox red at the oxidation. And pay attention to use the sequence ox red. We can write E of the cell equal E cathode minus E anode, or simply E of the cell is equal E plus minus E minus. The cell potential depends on the relative ease with which the oxidizing agent is reduced at the cathode and the reducing agent is oxidized at the anode. In other words, the cell potential of a reaction depends on the strength of oxidant 1 and the strength of red 2 that makes the reaction. At the standard state, the temperature 25 degrees Celsius, the pressure of gases is equal to 1 atmosphere, the concentration of ions in the solution is 1 m, 1 molar for each. So the cell potential is under the standard conditions and is called the standard EMF or the standard E0 of the cell. At the standard state, E0 of the cell is equal E0 of the couple oxide at the reduction minus E0 of the couple oxide at oxidation. So we have a difference between the notation of E of the cell and E0 of the cell. E of the cell is the cell potential of the reaction at the given conditions. E0 of the cell is the cell potential of the reaction realized at the standard state. So the potential of the cell is equal E oxide reduction minus E oxide oxidation. E of the cell can be found experimentally by using a voltmeter in the galvanic cell. So the question now, how to find the potential of the couple oxide. Consider the global reaction C2 plus Zn gives Cu plus Zn2 plus. This global reaction can be divided into two half equations, the reduction C2 plus to Cu and the oxidation Zn to Zn2 plus. So the two couples involved in this global reaction are Zn2 plus Zn and Cu2 plus Cu if we use the notation of the couple ox then rad. And the couples involved are Zn Zn2 plus, Cu Cu2 plus if we use the notation rad ox. If we write the half reaction and we start by ox to rad, the potential of this half reaction or the potential of the couple is E oxide, which is named the reduction potential of the couple oxide. And if we start from rad to ox, we can use the notation E redox, which is the oxidation potential of the couple. And to note that E oxide of a couple equal minus E redox of the same couple. But in electrochemistry, we prefer to use the sequence ox-rad. This is similar to the Ka and Kb of the couple acid base. A couple acid base is characterized by Ka and Kb, and Ka of the couple, Kb of the same couple are related. Ka times Kb equal Kw. But if we start with the base of the couple, we prefer to use Kb. And if we start with Ka with the acid of the couple, we prefer to use Ka. The magnitude of electrode potential depends on several factors. So E oxide of a couple depends on the nature of the electrode, so on the nature of the rad. It depends on the concentration of the ion in the solution, so it depends on the concentration of the ox, and also it depends on the temperature. For the global reaction Cu2 plus zinc gives Cu plus zinc 2 plus and divided into two half equation. In the first we start with the ox, so we put E oxrad. In the second we start with the rad, so we put E redox. The potential of the cell of the global reaction is the sum of the potential of the two half reactions, so E of the cell equal E of the couple Cu2 plus Cu plus E of the couple Zn2 plus, and as we know, E of Zn2 plus equal minus E of Zn2 plus Zn. So E of the cell is equal E oxrad of couple 1 plus E redox of couple 2, or simply is equal E oxrad of couple 1 minus E oxrad of couple 2, and we obtain the same relation mentioned above, E of the cell, E oxrad at the reduction minus E oxrad at the oxidation. The potential of a couple, we have to construct a galvanic cell between this couple in question and another couple that can serve, for example, as reference. So E of the cell in this example equal E of the couple oxrad reduction, so E of the couple reference, minus E of the couple oxidation, so minus E of the couple Zn2 plus Zn, and by this way we can calculate the potential of the couple Zn2 plus Zn. By convention, we assign a zero standard reduction potential for the reaction that serves as reference. 2H plus 2 electrons gives H2 gas, so this is the couple H2, H plus H2 as a reference, and the concentrations of H plus equal 1 molar, the pressure of H2 equal 1 atmosphere. In other words, the couple H plus H2 has a standard reduction potential equal 0 at the standard state. This is the reference in the electrochemistry. So consider the reaction in this example. 2H plus zinc gives zinc 2 plus H2. It can be divided into two half equations. At the anode, zinc to zinc 2 plus, and at the cathode, H plus to H2. Since zinc is a metal, so it can serve as electrode on the left side. But at the cathode, we have H plus, which is ion, and H2, which is a gas. So we need to use the platinum inert electrode. At the cathode, a platinum electrode in 1 molar HCl and bathed by hydrogen gas at 1 atmosphere, such as an electrode is called the standard hydrogen electrode, SHE, and has a value E0 of the couple equal 0. So since we could not measure the direct potential of a couple oxrad, we construct a galvanic cell between this couple and the couple of reference H plus H2, and we measure E of the cell. E0 of the cell in this example equal E0 of the couple H2, H plus H2 at the reduction minus E0 of the couple Zn2 plus Zn at the oxidation. And since E0, H plus H2 at the reduction equal 0, so in this case, the potential of the couple Zn2 plus Zn equal minus E of the cell equals minus 0.76 volt. In this table, we have the standard electrode potential at 25 degrees of different couples, and as E0 of the couple increase, the oxidant is stronger and the reductant is weaker. As E0 of the couple oxrad increase, so higher on the table of standard reduction potentials, that means it's a stronger oxidant, so the stronger tendency to be reduced. As E0 decrease, lower on the table of standard reduction potential, this is a stronger reductant and the stronger tendency to be oxidized. This is similar to the notation of the couple acid-base HA-A-. As Ka of the couple increase, the strength of the acid increase and the strength of the conjugate base decrease. So for a couple oxide, as E0 of the couple increase, the strength of the oxidant increase and the strength of the reductant of the couple decrease. Consider an example: cerium 4 plus, cerium 3 plus, VO2 plus, VO2 plus, FeC plus, and Fe2 plus. So cerium 4 plus, VO2 plus, and Fe3 plus are oxidant. Cerium 3 plus, VO2 plus, Fe2 plus are reductant. Since E0 of the first couple is greater than the second, greater than the third, so cerium 4 plus is a stronger oxidant than VO2 plus, stronger oxidant than Fe3 plus, and by the same way, Fe2 plus is a stronger reductant than VO2 plus, stronger reductant than Ce3 plus. As an application, calculate E0 of the cell for the following reaction at 25 degrees. First of all, we have to separate the global reaction into half equations. So the oxidation at the anode, we have Al transformed to Al3 plus 3 electrons. At the reduction, we have a transformation of NO3 minus to NO. Then we apply E0 of the cell equal E0 oxide reduction minus E0 oxide oxidation. So E0 of the cell equal E0 plus minus E0 minus equal E0 of the couple NO3 minus NO minus E0 of the couple Al3 plus Al.